Okay, thank you. So, so we have been going through some constraint optimization and unconstrained optimization theory and associated simple examples, and then application of those techniques in economic load dispatch problem solution. So the last topic that we covered was related to the Karush-Kohn-Tucker condition, that is in short KKT condition, which basically helps in solving unconstrained optimization problem with inequality constraint. Okay? So if you have any sort of inequality constraint like greater than equal to or less than equal to, then the KKT condition helps us in solving it. So we solved one example in the last class. Up to this point, slide number 33, we found a solution for the given problem, and we ended it there. So when we started the topic of economic load dispatch, we mentioned that the economic load dispatch issue can be or should be considered in the most practical manner. So then I say that, well, we will start with the most simplified version of economic load dispatch. By that, what I mean is this. If we go to slide 12, I mean this. In the blue text box, you see initially we will ignore generator limits and the losses. So our starting point was the simplest version of economic load dispatch problem, where we actually ignored the generation limits. Okay, but in practice, of course, the generation capacities should be limited by some upper margin and by some lower margins as well. And of course, because the generation should be part of, in the conventional power transmission and distribution system, you expect to have your transmission network installed, and you expect your conventional generations to be far away from the load centers. So that means you expect to have the transmission and distribution network in between your generation point and your load centers. So that means you expect to have some losses throughout your network. Okay, so this is where we are talking about the losses. Okay? You expect the real power losses and as well as the reactive power losses, because you are supplying AC power throughout the net using the network. So in the last class, we deviated from our initial assumption and we included the generator limits. Okay, we took help of the KKT condition and we tried to solve it. We got one solution. Today, what we will do, we will also look at the problem of economic load dispatch. Now we will also consider the losses. Okay, so today what we will do, we will try to formulate the economic load dispatch problem, including the transmission losses in the network. Okay, so this will be our starting topic today. So let's move on to slide number 34, ELD with the transmission losses. So this is one example system where you see, let's say you have n number of generating units. So we start from the left. Okay, so F1, let me use the annotation tool. So we have F1 here. F1 stands for the fuel cost for unit number 1. F2 is the fuel cost for the unit number 2, and so on. So we have up to, let's say, n number of units, generating units, supplying power. They are available units. Okay, they are available now. So they are able to supply power to satisfy the demand and the losses, because now we are considering or including the transmission losses in our ELD formulation. So the first block, you can consider it to be the boiler block. So in the first unit, you have a boiler. So you are inputting your fuel to your boiler. Then the boiler output is actually, let's say, the steam. The steam is running the turbine. So this triangular block is basically your turbine, representation of the turbine. The turbine blades are coupled with the generation rotating part. So let's say the circle is basically representing your generation, synchronous generation or synchronous generator. And the output of the generator will be your real power. So this basically, in this ELD problem, or in general, in the ELD formulation, we are more concerned with the real power loss rather than the reactive power loss. Okay, So ELD, economic load dispatch, deals with real power losses in the network. What about the reactive power loss? Should we not include it? The answer lies in another topic. So the reactive power loss minimization is basically covered in detail or taken into consideration in another topic, that is your optimal power flow. Okay, optimal power flow, which will be taken in some later part of our course. But in ELD, economic load dispatch, we are more concerned about the real power loss rather than the reactive power loss. Okay. So let's say the output starting from the fuel, F1, the fuel cost, we come up with the output from the generator, that is the P1, that is being supplied to your transmission network. This rectangular, big rectangular block is basically your representation of the transmission network. And at the other end of the right hand side of the transmission network, you have the, let's say, the summed up load, okay, or the simpler representation of a single load, which is the demand, the total demand from all the loads that could be connected at some instant to this transmission network. That is your P load, total demand for all these units. Okay. So similarly, you have F2 representing the fuel cost for generating unit 2. Again, the first square block, this is your boiler unit for unit number 2. Then the second triangle here, this represents the turbine unit for your generating unit number 2, and so on. Okay. Any question up to now here? Any explanation required here? Okay, so I will proceed. The next, let's formulate the ELD. So our objective is to minimize the total cost. Okay, so again we are taking the cost function Ci for the ith generator, and we are considering, let's say we have m number of units, small m number of units, so it will be summation of all the C's, okay, starting from I equals 1 to m, and all the C, the cost functions, individual cost functions, ith for the ith generator is only dependent on its own generation or its own real power generation. So you see Ci is only a function of PGI. Okay, it's not a function of PGI up to PGM. It's only a function of PGI. So we have the constraint now a little bit modified or updated, we can say. So remember the first case we considered for ELD, we only had summation of PGI was equal to PD, but now we have included the P loss. Okay. But again, we are not taking here the limits. Okay. We are not taking or considering here the generation limits. But now we know how to tackle the limit issues. Okay, we have to apply the KKT conditions. So in general, the most general case should be that you consider these losses here in the equality constraint, as well as you consider some inequality constraint. But here I'm showing you the example of where I'm not considering the limits, but I'm considering the losses. Okay. So again, to solve this problem, we have already formulated the ELD. So again, you formulate the Lagrangian. Okay, remember the Lagrangian was formed like, first the cost function will come, your original cost function. So this is your original cost function CT plus, because you only have the equality constraint now, so you will only use the lambda, the Lagrange multipliers, and then you rearrange your equality constraint in this fashion. That means, we go back to the last slide, so you rearrange it like this. The summation part will be like appearing in this expression as a negative. Okay, so PD plus P losses minus summation of PGI should be equals to 0. So this is what is written here. Okay, the formation of the Lagrangian is done. Then you have to take the gradients, okay, as before. So if you take the gradients, before, you see you did not have P losses. Okay, previously you did not have P losses, but now you have this additional term. Okay, now any intuition, okay, anyone can tell how can we represent this P loss here? In general, what is P loss dependent upon? In general, for any, let's say any electrical network, you are trying to represent P loss by some equation, mathematics. How do you represent it? Real power loss. Anyone?
Can you please repeat the question?
Repeat. Okay, let me repeat. The question is, can you represent P loss by any mathematical expression? What is P loss? P loss is basically the real power loss where it is happening.
Loss.
Yeah, this is basically I square R loss. This is what I'm asking for. So this is nothing new. Basically, we already know how to represent the P loss, right? We can represent P loss simply by whatever current is being flowing through the network in each of, let's say there is a big network, interconnected network, okay, many transmission lines, and they are connected with each other like a web. So if I know the current flow through each of the lines, okay, let me draw something like this. Okay, let me say this is something like this. This is bus, this is another bus, okay, this is another bus. So like this, okay, let's say this is a big network, and ultimately let's say this is connected to a load. Okay, this is the load bus. So similarly you could have many other connections here. So what I'm saying, and what the answer was, basically, if I know the resistance of these lines, okay, transmission lines, and if I know the current flow through these lines, then I can simply calculate I square R, right? So this is one way to represent the P losses. Problem is that in our ELD formulation, have you got the appearance of I, the current, in any of the equations till now? Have you seen I, presence of I, current?
No, sir.
No. So we have only come up with some P's, right? Real power generation. We are only bothering about real power generation. Now, can we represent these I, okay, whatever I is flowing, let's say, through these lines, can we relate those I's with the corresponding P's, all these P's? I mean, are not they the functions of these P's somehow? Because if you don't have any P, if P is zero, let's say all P's are zeros, there is no power generation. Do you expect any I to be present here? No. That means if you don't have any generation, basically you don't expect any current flow and any power losses. So that means there should be some way to have some mapping between P, any P here and any I here, right? Usually you can use some sort of Ohm's law, okay, V square over R or P square. You know, the P and I are related in Ohm's law, in one form of Ohm's law. Okay, in general it is P equals to VI because we are considering real power loss. So simply you can write P equals to VI, P equals to I square R. There are some ways to represent I, and to relate the I here in through these networks and the corresponding P's here. Okay. And of course, whatever loss is here, whatever loss is occurring here, of course, it should be some portion of the generation, right? It is not beyond the generations. So that means if, let's say, this is 100 megawatt here, this is 200 megawatts here, this is, let's say, 50 megawatts here, the losses occurring throughout all these network elements should be some portion of this 100 megawatt, some portion of this 200, and some portion of this 50, right? So in a sense, we can say that we can also represent these losses here. Okay, these losses, whatever is appearing, we can also represent it in terms of the power generations. Is this clear? Should I repeat?
Okay, sir.
So okay. So in short, what I mean is the losses can be represented in terms of generations. Okay, because losses are nothing. It is nothing new other than the generation. It's part of the generation actually, because generation is something which is being distributed throughout the network and which is used basically to supply the load demand and the losses. So we can relate these generations with these losses very easily. So this relation is basically known as the transmission loss formula. Okay, the transmission loss formula, which relates the losses throughout the network and the generations available for the network. So what is transmission loss formula? This relates with the generation of the network and the losses in the network. This is transmission loss formula. Okay, so let us see how does it look like. What is the nature of this transmission loss formula? Let us see. What I'm saying is that I can represent these losses by some function of PGI. So that said, we will look at the equation in probably in next slide or the second next slide. But what I want to say now, that means you can have some partial differentiation of these P loss with respect to the generations. Is it clear now why I discussed all these things? You expect to have some value, non-zero value here, while you take the partial derivative of the loss function, loss equation, with respect to the corresponding generation. Is it okay?
Yes, sir.
Okay. So this is why I said all these things till now about the relation between loss and generation. So simply you take the gradient and you get this, and you equate it to zero. This is the condition for necessary condition, first order necessary condition for obtaining a minimum, or sorry, an optimum. So then if I keep on calculating or manipulating these equations, then what I get, simply I get dCi over dPgi, and I take the lambda here. You see there will be a minus lambda here, and the second portion will become positive. So I have lambda multiplied by di P loss. I have lambda multiplied by this, and that will become positive here, and then this lambda would be taken to the other side. So from the first gradient, that means taking the gradient with respect to the x variables. Remember, x are the unknown variables. Okay, a vector of x. That is f, the variables within the f function. Okay, this is gradient with respect to, you can say, x variables, di f over di l over di x, and then you take the second gradient. What should be the second gradient? Second gradient is basically with respect to lambda. So this equation will come if you take di L divided by di lambda. Okay, so this equation will come, this second equation here, the last equation of this slide. This will come when you take di L over di lambda. That means simply you will get this, whatever coefficient is multiplied with lambda, because I am taking partial derivatives, so everything other than lambda would be treated as some coefficient, constant coefficient. So that will arrive here, and you equate it to zero to find out the optimum. Clear? And these two together gives me, this set of equations gives me the so-called coordination equation. Now we need to know what is basically the P loss, expression of P loss, explicit expression of P loss. So let us see. Okay, before that, there are two approaches being listed here, although there are actually many other approaches, but probably in this course, we will be focusing on the loss formula method, which will be taken here as an example. And the second method, second approach for this is the optimal power flow method, which will be taken in some later topic. Okay. Of course, there are other methods. Okay. The list is pretty long, not so short. But in this course, we will be focusing on these two. And for this topic of ELD, inside the ELD topic, we will be taking this loss formulation method as our solution method. Okay. So let's take an example. So the example is this. For a 3-generator system, we have 3 units available. These are the cost functions in the form of alpha I plus beta I PG I plus gamma I PGI square, and so on. So we have 3 generators available. You have the total demand, 850 megawatts. Now you see a simplified loss formula, transmission loss formula is presented here. which is basically a function of all the powers, which is quite logical, right? Because every powers are contributing to some portion of the total losses. Okay, there is some contribution from generation 1, there is some contribution from generation 2, there is some contribution from generation 3. Of course, there are more complex expressions for this loss formula, but we are not taking it in this course. Okay? There are much more complex formulas available for this transmission loss presentation, but for the time being, we will do with this. Okay? Of course, there are some other more complex representation of the losses. So you can see that the loss expression is basically a quadratic function. Okay, a quadratic function. You see this PG1 square, PG2 square, and PG3 square, summation of all these. So this is nothing but a nonlinear expression or a quadratic expression, which is quite logical because loss is some sort of quadratic expression. Okay, so then we already derived the coordination equation. This is the first part of the coordination equation. Okay, dCi over dPgi equals to lambda into 1 minus dip loss over dPgi. We just check back. Basically, what we are writing is this. We are writing it like this equation of the gradients. dCi over dPgi is equal to lambda into 1 minus this one. Okay, we are writing it like this. This is the first equation from the coordination equation. So we are writing it. This is the generalized form. Then if I do the calculation, okay, if I perform the calculations, dCi over dPgi for generation number 1, from where do you get that? You know the expression of C1, which is a function of PG1. So you simply take the derivative, first derivative. Okay. So the expression is this, 561 plus 7.92, and this. So if I take this dC1 over dPg1, simply this is a constant, so this will vanish. This will remain only 7.91, Pg1 will become 1, plus 2 will come multiplied by 0.00156 to Pg1. This is how we do it. Okay. So this is what is done on the left hand side. Similarly for the second equation of C, and similarly for the third equation of C. Okay. Then this should be equated to lambda 1 minus, now you also know the expression of P loss, okay, which is a function of all of the generations, Pg1 square, Pg2 square, and Pg3 square. So simply you take dip loss here. Simply you calculate the partial derivative of this dip loss divided by dPg1. So what will remain? Simply 2 into this multiplied by Pg1. So this is what is remaining. So you have lambda multiplied by 1 minus 2 into whatever Pg, whatever was the coefficient of Pg1 square in the loss expression, that will come here. So similarly, you can calculate this, and you can also calculate this. So these three are basically the outcome of the single equation, which is in vector form. Okay, you see dCi. Okay, so it is in vector form. You have 3 generators, so you will get 3 equations. And from the second part of the coordination equation, remember the second equation in slide number 36, this was the second equation. You simply write this PD plus P loss minus summation of PGI is equals to 0. So this is it, PG1 plus PG2 plus PG3. This is the summation of PGI minus P demand. This is your 850 given in the question, minus P loss. This is unknown. Okay, you don't know P loss actually till now. That should be equal to 0. Now this set of equations, unlike the first case of ELD, in the ELD there was no P loss. Okay, so simply you had to solve 4 equations and 4 unknowns. Those were linear equations. Okay, so you solved for PG1, PG2, PG3, and lambda at this stage from these 4 equations. Those were linear equations. However, the problem here is that these are non-linear equations. Can anyone tell why these are non-linear? Can anyone tell why these equations are non-linear?
Because these are quadratic, they represent quadratic equations.
Excellent. So P loss itself is a quadratic expression. Similarly, you see there is a multiplication between two unknowns. Lambda is one unknown, PG is another unknown. You cannot separate them. So this is another nonlinearity. So the nonlinearity is arising from the P loss itself, because this is a function of PG1 square, PG2 square, PG3 square, which are on their own, which are nonlinear, as well as from the top three equations here, where you have lambda and PG1 multiplied, lambda and PG2 multiplied, lambda and PG3 multiplied. These are also nonlinear. So the nonlinear equations, you can't solve them simply using the matrix or linear algebra. Okay, these are not linear, so you can't apply linear algebra techniques. So what to do? You have to go through some numerical methods or some iterative techniques. One such technique is basically your loss formula, okay, which we will take today as an example, a solution of this sort of problems. The loss formula method basically helps us to solve this sort of nonlinear set of equations for economic load dispatch problem. Another way to solve this is optimal power flow, which, as I said earlier, will be taken later on. So let's go through the steps how to do this. Remember, this is some sort of iterative technique. Okay, so for like any other iterative techniques, here again you have to take some starting values, some guess, okay, some assumptions. Okay, but those assumptions should not be arbitrary. What we will do here, you see, step number 1, you pick a set of starting values for PG1, PG2, and PG3, which equals only to the load, not load plus losses. Okay, so that means these values are not the final values. Do you get my point? Your equality constraint equation, remember, if I go back, slide 35, you see the summation of generation should be equal to the demand plus losses. But in the loss formulation, in the loss formula method, the solution technique, to start with, it doesn't consider the P loss. That means actually we are taking some guess, okay, by neglecting the losses to start with, because you don't know the losses. So you can't have any assumption for the losses. But you know the demand. So you can take some calculated guess, I say, calculated guess for the 3 PGs, okay? 3 PGs. Remember, we don't have the limits on the PGs here, okay? We don't have the limits, but in this step, okay, in the loss formula method, if you have the limits given in the problem statement, whatever value you pick here, okay, in the step number 1, the values of PG1, PG2, and PG3 should be within the limits. But not for this example. In this example, we are not including them. Is my point clear? If you have the limits given, the starting value you pick should be within the limits. That is quite logical. But here, because you don't have the limits stated in the main problem, so you don't have to bother about the limits. Okay, you can start any values. Okay, let's say for example, if you have demand is 850, you can simply choose 850. You can give it to PG1 and simply take 0 and 0, because you don't have any limits to satisfy, right? So simply you take PG1, 850 plus 0 equals to the load. I think the point is clear. Okay, but if you have the limits, then you choose the limits, choose the values here. You pick the starting values in such a way that all of them satisfy the upper and lower bounds. Okay, and at the same time they sum up, they add up to your load demand. This is a guess. Okay, this is a guess, a calculated guess. Step number 2. So the iteration basically starts from step number 2. Step number 1 is just, you can say, some sort of initialization to the problem, to the iterative technique, some sort of initialization. So now, because you have guessed the values of PG1, PG2, and PG3, you have the guess available. Simply you can calculate this dip loss by dipgi. Okay, dip loss by dipgi. Because P loss is a function of PG1, PG2, and PG3. Now you can calculate dip loss by dipg1, and you can put the assumed value for PG1 there. You can calculate dip loss by dipg2, and you can put the value of you can put the value of Pg2, assumed value of Pg2 here. Similarly, for di P loss over di Pg3. We'll solve it and then we'll show what are the steps basically means. Okay, a point to be noted here at this step that the incremental losses, that is this expression di P loss by di Pgi, these incremental losses and the total losses, which is P loss, will be or should be considered constant until we return to step 2. As I said, step 2 is a part of iteration. So that means in step 3 and 4, you should assume that your incremental loss and the total losses are constant, okay, until you come back to step 2. We'll see how this happens in the example. Step number 3, then you calculate the value of lambda such that now you see we are including the losses. In the very first step, we did not have any idea about the losses. So we simply took one guess and we equated Pg1 plus Pg2 plus Pg3 equals to the load. But now we have some idea at least about the losses, although it's not perfect, but we have some knowledge about the losses. So we add them with the PD and we try to equate them with this Pg1 plus Pg2 plus Pg3, and with this knowledge we try to calculate the value of another unknown, remaining unknown, which is the lambda variable. Okay, so now what we do, we compare the Pg1, Pg2 and Pg3, compare the Pg1, Pg2 and Pg3 from step 3. What we will see at this step is basically with this update. Okay, you see it's being updated. Initially we started with only the balance between Pg1, Pg2, Pg3 and the demand. Okay, now what we are doing, we are again rewriting this expression which we used at the top, but now we are taking help of some additional term. So of course there will be some effect on these values also. Okay, these values here will be also changing compared to these values. I will show it in the example how they actually change. Okay, so at step 3, basically what we will get, we will not only get the lambda value, but we will also get some updated values for Pg1, Pg2 and Pg3. Why? Because now we have some updated expressions. At the top in step number 1, we did not include P loss, so there were some balance between Pg summation of Pgi and load, but now you see we have some losses also. So these values of Pg1, Pg2, Pg3 at step 3 should not be exactly same as the starting value. Okay, as the starting value, because we are introducing some losses here. So of course this balance will be a little bit changed. It will not be exactly as it is. So whatever Pg values you get at this step 3, you compare it with the immediate value, the previous iteration value for the Pg1, Pg2, Pg3. Okay, so the current iteration value for Pg1, Pg2, Pg3 will be compared with the immediate past value for Pg1, Pg2 and Pg3. If they are very near, okay, if their difference is very much negligible, then you stop. Otherwise, you go back and you calculate again the losses, the incremental losses, and the loop will continue. Okay, this slide is probably a little bit confusing and boring. Let us take the example directly, okay, and apply all these information there step by step. Probably that will be nicer. So let's apply the steps. Remember, our total demand was how much? 850. Okay, it was given in the problem statement in slide number 39. In slide number 38. Okay, this is P demand 850. So what should be step number 1? You should choose Pg1, Pg2 and Pg3 in such a way that if you add them, then you reach at 850. Okay, so these are chosen again arbitrarily because we have not considered any limits on the generations. So you simply choose 400, 300, 150. You can start with any other values, considering no limits are given. Okay, you can start with any other values, but of course they should sum up to the demand. So you add them up, 400 plus 300, it is 700 plus 150, so it is 850. So the condition is fulfilled at step number 1. Now we enter the iteration, step number 2. Now we calculate the incremental losses and the total loss. Okay. So what are the expression for incremental loss? You simply calculate die P loss with respect to PG1. You take the partial derivative of P loss with respect to PG2, and you take the partial derivative of P loss with respect to PG3. Okay. So you know the expression of P loss in this given in slide 38. So it's very simple. You simply calculate die P loss by die PG1. What will you get? If you calculate, yeah, anyone, what will you get if you calculate die P loss by die PG1?
2 into 0.03.
Yeah, 2 into 0.00003 PG1, right? Similarly, you can calculate die P loss over die PG2 and die P loss over die PG3. You have some assumption for PG1, PG2, and PG3. You simply plug them in. This is what is done. Okay? This is what is done here in slide 41. So you see 2 into whatever coefficient was there in the loss expression multiplied by PG1. And this is the value. 2 into the coefficient there and PG2. 2 into the coefficient into PG3, and you get it. Okay. Then if you know this, and this, what is P loss? P loss is simply you put here, okay, PG1 squared, that means 400 squared, what is this, 300 squared and 150 squared, and you add them up. Clear?
Yes, sir.
So this will give you 15.6 megawatts. This is step number 2. Now we go to step number 3. Remember, now we have to incorporate the losses in this equality expression. It is no more summation of PGI equals to PD. Now we have some information of P loss, although not, 100% correct, but we have some value. So we will put it, okay, we'll put it, and we will try to get the updated values for PG1, PG2, PG3, as well as the value of lambda. So how do you do that? You use now these expressions, okay? You see these expressions in slide number 39. We obtained these from the coordination equations. So you simply plug the values of PG1, PG2, PG3. You plug the values for P loss, and you solve for the left-hand side, PG1, PG2, PG3, and lambda. So you have 4 equations and 4 unknowns. There is a little trick, that is we are only we're only replacing the PGs on the right-hand side, which are part of the loss expression. Okay, these are part of the loss expression, right? So we are only putting the PG values, assumed PG values from the previous iteration, you can say. So the previous iteration PG values will be put here, and the new PG values will be obtained after solving this. Is that clear?
Yes, sir.
Simply you can write PGI of, let's say, I plus 1. If I is the iteration number, then this should be PG1 I. So PG values at the ith iteration will be put here, and PG values for the I plus 1th of the next iteration will be obtained after solving these 4. So let's see how it is done. So simply you see in the right hand side of those equations, we have put the PG values and we have calculated this. So now you see these are linear equations. Okay, the 4th one, you don't have P loss, rather instead of the expression of P loss, you have some numerical value for P loss. So you have got rid of the quadratic term. Okay, instead you have simple numerical value. So now you can cross check. You see only in this expression you have PG1 as linear function of lambda, PG2 linear function of lambda, PG3 linear function of lambda, and summation of PG1 and PG2 and PG3 is this. So now they are in linear form. Okay, so we can simply apply our linear algebra knowledge, and you can solve these 4 equations, 4 unknowns from these 4 equations. Which are the unknowns? PG1, PG2, PG3, and lambda. So these PG1, PG2, PG3s are the next or current iteration values, and the ones that we have put here, this should be taken from the previous iteration. Okay, these are the updated values. You can simply updated values or old values and new values, whichever is easier for you. So we continue with step number 3. Simply form the matrix. You four equations you have: number 1, number 2, number 3, and number 4. 4 unknowns: PG1, PG2, PG3, and lambda. Simply form the matrix and take the inverse of these 4 by 4 matrix. Take it to the other side. Get the inverse. And you solve for the 4 unknowns. Okay, so these PG1, PG2, PG3 are the updated values, and at the same time you have obtained the value of Lagrange multiplier lambda. Okay, so you see they are updated. We started with 400, 300, and 150. Now you see these are updated. Okay, all of them are updated. Now the question is, okay, first thing is that they are different from the previous value, right? We started with 400 here at PG1. This is pretty near. We started from 300, but it is 299. It is pretty near. But this is again different by 25 megawatt. This is again different by 40 megawatts. So that means this is a significant change, okay? Significant update. So we have to continue. So now you go back to step 2, and your now old values will be this, and you will be looking for some new values following the same steps. Okay. So step 4, we check, okay, the condition that I mentioned just now. Since the values for PG1 up to PG3 are quite different from the immediately previous values, we will return to step 2. Now we calculate the incremental losses and losses considering the new values of PG1 up to PG3, okay? Same process. So now you see we are putting, instead of 400 here, we are putting 440 something. Instead of 300 here, we are putting 299 point something. Instead of 150 here, we are putting 125 point something. And we, with the updated value of P, we can calculate P loss from the expression of P loss. And then we continue to step number 3. Again, on the right hand side of the coordination equation, the first 3 coordination equations, we use the current values of PG1, and we are looking for the updated values of PG1, PG2, PG3, and lambda. And here you see we have put the updated value of P loss in the equality constant. Of course, demand remains same. Demand remains at 8 feet. So let's continue with the next step. We discontinued again. You formulate the 4 by 4 matrix because you have 4 unknowns. You take the inverse of this, take it to the other side using the inverse. And now this is your result. I mean, this is the updated value of PG1, PG2, PG3, and lambda. Okay, so still, what was the previous value? Let's check back. The previous value was 440 for PG1. Now it is 433, so 7 megawatt. This is more or less same. It was 299 point something. It is 300. PG3, how much was it? Previously it was 125. This is 131, so 6 megawatt. Still, it is not, I mean, megawatt is not a small value, okay? It is a big value, big change from the previous value. Of course, lambda is updated. So what to do? You carry on with the iteration. There are some steps given for the iterations, and you do this, you continue this until and unless you have very small variation between 2 consecutive iterations for the PG values. Okay. So iteration 1 and 2 are actually done by hand. Then 3, 4, and 5 are not shown, but you can do it. You can do it by hand or by some MATLAB coding or by any other programming tool. So you see we stop at 5th iteration ultimately for this example problem. Why we stop? Because you see 430 in iteration number 4, it is 435.87, the PG1 value. Now in iteration number 5, it is almost same. Okay? It is fraction of a megawatt. Similarly here, PG2, and similarly here, it is fraction of a megawatt. So that means we are in a position to stop. So this is your final solution for this loss formula method. Okay. Now, any question? So this is the end of economic load dispatch for this course. Of course, the economic load dispatch is, I mean, it is not a topic which you can end discussion on because it is a research topic, and there are many variants for this economic load dispatch because you're in the final year, I mean the final semester actually. So you should have some idea about what is next in the economic load dispatch. Okay, what is next? But till now, okay, till now, any question about this example problem?
Yeah.
Yeah.
You have mentioned about something that will be constant from step 2. I did not get it because you said that you will explain it later. And I didn't see where you explained that.
Okay. By this, what I mean is this. I mean, if you go to the steps, probably you are talking about this incremental losses and total losses. Is it this?
Yes, sir. Yes.
Okay, so you can check. I mean, whether this statement is true or not, you can check on your own. Okay, whether we have changed these losses until we have returned to this step. So you see these loss. Okay, let us go back to the step. This is the first step 2. Okay, the first iteration for step 2. Okay, so you have calculated the loss 15.6. These are, remember these numbers. Okay, can you remember 0.0240, 0.0540, and 0.0360? Okay, at least we can remember this one. This is easier, 15.6. So what that specific line or that specific step says is, until you go and reach the next iteration, step 2, you have to keep these values constant. Okay, you don't change them. I mean, because you are changing the PG values, so but you're not changing the P loss values until and unless you reach there. Okay, so using those values, basically, you see, this is 1 minus di P loss by di PG1, remember here. So what is that? That is this value, 0.0240. So in step 3, we are actually taking the value of that di P loss by di PG1. We are taking the value of di P loss over di PG2 here, di P loss over di PG3. And we are taking that loss that is calculated here, 15.6. These are not varying until and unless you go back to step 2 and recalculate them. This is the simple meaning. There is nothing special. Okay.
Yes.
So they are only updated after you have updated the PG values. You have got the new PG values here. Only then you are updating them. In the next iteration, you are updating them using the new PG values. This is what it means. And you're also updating the P loss. Until then, they are taking any calculations in between for any intermediate calculation steps. You are simply taking the previous values. Okay, this is what is meant. Yeah, thank you. Any other question? No question. Okay, so if you don't have any question, let me stop the discussion for our syllabus, I mean the ELD syllabus for this course. But as I said, it is not easy to end the discussion. Now, as I said earlier, there are several variants for this economic load dispatch. Let me try to touch some of those, okay? Just touch some of those, few of those. What we have done here, you see, we have taken the example problems purely or specifically related with the thermal power plants, right? These are the cost curves, input output curves for the thermal power plants. What will be the solution process if instead of the thermal power plants, your power station is only having the hydro power plants? Because you see, why is this important? How to tackle that issue? Because you see, this is fuel cost, right? Fuel cost curves. What is the fuel for the hydropower plant? And what is the cost? Do you have to buy water to feed it to the hydro turbine or pass it to the hydro turbine?
No, sir.
No. So that means the hydro unit, if you have the hydro units in your economic load dispatch problem, you can't simply follow the same process. There should be some different mathematical expressions to represent the economic load dispatch problem associated with hydropower plants. Am I clear? So the hydropower plants, you can't solve it in the same way as we did because the cost curve is not there, but there should be something else. There should be some other constraints or some other sort of cost functions which you will target to minimize or maximize or optimize, I should say, to solve the economic load dispatch problem, right? This is if you have purely hydro, I mean, only a power station purely built up of hydro units. What will be the decision next? Okay, next issue. What will be the decision? Let's say if you have both hydro and thermal units. So you have some portion coming up from the thermal units, you have some portion coming up from the hydro units. How do you coordinate them? This is the next question. This topic is covered, this question is answered in another topic known as hydrothermal coordination. That is another chapter, but that is not included in our syllabus, but this is another interesting thing. If you have a mixture of generation, okay, if you have some hydro and some thermal or conventional thermal units, how do you incorporate or how do you solve the economic load dispatch? How do you share the loads among them in the most economic way? This is another question that is covered in hydrothermal scheduling or scheduling. Next question, nowadays, or not specifically nowadays, but the global warming issue is a, I mean, long discussed and long disputed issue. So with the help of these thermal power plants or fossil fuel based power plants, what is the problem? One problem is that you are emitting the carbon based gases, okay, carbon dioxide, carbon monoxide, nitrous oxide, okay, a family of nitrous oxide gases, and those are thrown into your environment, and those are one big cause for your air pollution, okay, environmental pollution. So another way of looking into the economic load dispatch could be that can you go for some minimum emission dispatch, okay, along with the minimization of fuel cost, okay, along with the minimization of fuel cost issue. Remember, all these are not part of your syllabus. I'm just putting these words just for your interest, okay, just for your interest. So if you don't understand this part, so don't be too upset, okay. These are just for your future interest, that what are the other ways to look into the economic load dispatch problem. Okay, so what I'm saying is basically what we did, we considered only these cost functions, right? Fuel cost functions for, let's say, our thermal power plants. Along with these, can we formulate or can we introduce some other constraints or some other sort of costs associated with our emission? Let's say if the emission is, could the emission be expressed in terms of generation, like we represented the fuel cost in terms of generation? Okay. There are ways, and that is covered in minimum emission dispatch. Minimum emission, that means you are looking for that combination of generations which minimizes your cost. Not only minimizes your cost, but at the same time it also take care of minimum emission of harmful gases, okay, that is known as minimum emission plus minimum cost economic load dispatch. This could be another topic. Then you also have nowadays, because of this emission problem, what the researchers are doing, they are shifting their focus towards green energy, alternative energy sources. They are looking towards the wind energy or the solar energy or biofuel or wave or ocean. I mean, there are different categories of renewable energies, right? Sustainable energies. So instead of using 100% thermal power plant or 100% hydropower plant, if you plan to incorporate some sort of wind energy penetration, if you want to have some energy from your wind source or some energy from your solar source, then how this ELD problem will be more, I mean, modified, how you have to modify this and how you are going to solve this. So these are, in short, some of the variants of the economic load dispatch. So that what in summary I want to say, this is not the end of economic load dispatch discussion in this course. This is, you can say, only the starting point in the undergraduate level. There are many more things and many more interesting things to deal with in the current scenario, current power system scenario, or current power supply scenario in today's world. Okay, many more interesting things. And lastly, these are I talked about the source end. Okay, what about the, I mean, if I change the source, what we should do? Another way to look into this ELD problem, if we think little differently about the solution techniques. Okay, nowadays you have fast computational techniques, and people are coming up with some newer and newer optimization algorithms. They call it nature-based optimization algorithms. So instead of using the loss formula method, instead of using the Lagrange multiplier method, instead of using the KKT-based method, there are other ways to solve this. But these are the most classical ways to create your basic understanding for solving the economic load dispatch problem. These are only the basics. This is not the advanced level, because this is the basic level course. So you can also go for different optimization algorithms, different optimization techniques to solve these sort of problems. Okay. So with that, I will finish this topic today, and I will just touch the next topic just to give you some flavor of unit commitment, and then I will continue inshallah from next week. So to finish with this topic specifically, our syllabus will be up to this slide. Okay, it will include the optimization slide and the ELD slide and the introduction slide. So 3 slides. I will update the slides because I posted earlier 2 sets of slides, probably on optimization and ELD, but those were not updated. So I will update it inshallah by today. So go through the updated slides, please. Okay. And of course, the video lectures will be very helpful for your preparation, I hope. Okay. Any other question on ELD, economic load dispatch? If not, then I will switch over to the next topic. Just I will introduce a few things and then I will stop because I have only 10 minutes. Probably I will take 5 minutes.